All right. Good morning. Let's see. We are continuing chapter 6, right? I'm not going to talk too much about programming assignment 4 yet because I assume many people have not started. But if you have questions, come to office hours and we'll talk more about it. We left chapter 5 behind and moved on to chapter 6. Just a few things about this chapter. If you've taken Math 110, there's a lot of review here, which is great for you. But don't underestimate it. There are some new things. But in general, what we're going to do today, for example, is enormous. It's really exactly 110. I don't think you do it quite that detailed in Math 54. But even then, you see these concepts. I think this will feel more comfortable to you than the previous material. But again, don't underestimate it. I will emphasize what's special for numerics. But let's review what we did last time. I didn't quite cover pivoting. And then today is just usual matrix properties and Math 110. Linear systems is one of the main concepts of linear algebra. We want to be able to solve things of this form. Why do we want to do that? Because they show up everywhere. If you wonder if the world is linear or not, you know something that can answer that. Many problems are nonlinear, but the way you solve them is by turning them into linear problems, like in Newton's method. Most of the big supercomputers up on the hill or anywhere, they are spending most of their time solving these things with various properties. I can't emphasize enough how important this is. This is what computers do, because we turn most problems into this. Least square problems we don't have time to cover in this class, but they also end up in these types of formulations. So we want to be able to solve this. You learned it, as I said many times, probably already in high school, at least for 3x3s. You learned the process of Gaussian elimination, which is this idea of doing operations that turn it into something we can solve. I cannot put it into big concepts because in this class we don't teach other methods. But I still want to tell you that if you do more numerical analysis, there is a whole class of method called iterative that works quite differently. But these direct methods are such that you do a bunch of weird operations where you put zeros here, right? You turn it into an upper triangular system, and then you keep on going. And I think the point I want to make is that it's exact when you're done. It's not like Newton's method that you make an iteration and is it close enough? No, let's do one more, right? It's not that type. So these are direct methods, and they are generally considered, of course, these are the classical methods. These are what you learn for small systems. This is the way to go. But there are pros and cons that we don't have time to cover. Anyway, so how is Gaussian elimination described? You can describe it by 3 properties that are pretty obvious, because remember, these are, even if we write it as ax equals b, they are n equations, linear equations in n unknowns. Okay? And the columns of that matrix A, are, of course, correspond to the numbers that you multiply each of the unknowns by. But each row corresponds to an equation. Okay? What is an equation? It's something equals something, which means that if you multiply it by any lambda non-zero, it's still the same equation, still has the same solution. All these 1, 2, 3 here have the property that it doesn't change the solution x1, x2, x3. Okay? So that's pretty clear. Adding another equation you might have to think about, but clearly if A is equal to B and C is equal to D, you can add them. So A plus C is equal to B plus D, right? That's pretty clear. Finally, switching rows, that's so obvious when you do it by hand that you don't even think about it, but because it's just an equation. Who told you what the order doesn't matter. But in the terms of the matrix, maybe it's a little weird that we can just flip rows, but we can. Gaussian elimination is really described in this sentence: reduce a linear system to triangular form, where we will define triangular later on today, actually, but it's pretty clear what it means. It means that you have zeros below the diagonal of the matrix. You do it by doing these elementary row operations in a certain way that is not described by this sentence, but you know it. You compute appropriate multipliers lambda, and of course these EJs will always be the pivot row that you subtract away. What do you do when it's triangular? You identify that then it's easy to solve. Because the triangular system, there is one number that is very easy to get, namely the last one. And when you have that, you go back up. These are the processes. Let's come to row exchanges in a little bit. But let's just talk about the algorithm. Even though you know it, and I think I did assign some simple exercise on that, I think it's what I will emphasize here that we'll not learn in Math 110 or Math 54, of course, is how do you actually turn this into computer code? So let's focus a lot on that. Even if you think you know Gaussian elimination back and forth, I'm sure you would I have to think a little bit about the details in this algorithm. And we did it last time. We implemented a little function called Gauss elim no pivot. This is on the web page, but with this pivoting thing that we'll talk about more today. Just in terms of computer, we grab the size of the matrix. It's there. You just look at it. That's not the big deal. The fundamental structure here is, of course, important to realize. What is I? I is the row that you choose for pivots at each step. So remember, we have a typical step in this process would mean that you've done this row you never touch. You all know that. Unless we do row exchange, we're not there yet. We never touch that row. It's fine. Remember, we just want to put zeros below, right? And let's say, and this is the triangular form. So at a typical step, I would say we've come this far. Let's say we haven't done anything to these. And we've started introducing zeros here, but we have these guys left, right? So this is a typical scenario that you choose a pivot row. Right now, the pivot row would be I equals 3, right? Okay, so this is the outer loop. So the first thing you have to decide is that clearly the outer loop here is that you start with this row as pivot, then you do this, then you do this. When you come down to this row, you set this guy to 0, and you're done. So therefore, we don't go to n. If you code it well, you could probably go to n and have an empty do nothing thing. But the right way is you really pivot rows go down to n minus 1. And we call them I. Okay? So for I, 1 to n minus 1. Then what? Then you want to zero out. So when you have a pivot row I equals 3 here, you want to zero out everything below. What is the first one? That's going to be not 3, but 4, right? So now I'm talking about a j, which is the equation. In this example, it's 5. It's the equation that we're right now working with, right? Where is it going to go? It's going to go from I plus 1 all the way down. I plus 1, that's that loop, right? And now we can start doing the elimination. And then, of course, now we start actually doing a calculation. And that calculation is, how do we set this guy to 0? We do it by subtracting a multiple of the pivot row, pivot equation. And that multiple is exactly chosen to be that divided by that, because when you then subtract this number, this will become 0. That's what Gaussian elimination does. So that multiple we call m, and we just calculate it. And then what? Well, as I said, this by design will put a 0 here, right? So you could just put the 0 there if you want to. But more generally, of course, you have to take the whole equation minus m times the whole pivot equation, right? And in fact, there is a b here as well. B. And it has no structure, but the whole equation and b has to be subtracted. You have to subtract the pivot row from that. Okay, so how do you do that? Well, you could think about it this way. This is, of course, also column I, right? Because remember, this was I comma I. That's the pivot element is I comma I, right? So when you want to subtract this whole row from there, you want clearly it's a new index. It's one more for loop, right? And we call it k. And it has to go from I all the way to the n, to n. So this explains the next for loop. For k equals I to n. And what is the operation I'm doing? Now is the actual elimination. You take elements. So let's say we're standing at, we might be standing over here at k equals 5. 3, 4, 5. That's bad because it overlapped. Just a coincidence. We might be standing somewhere here. You want to take this number minus that number times m, right? That's what it means. And this number is, of course, j comma k. So I'm doing a of j comma k equals a of j comma k minus m times this guy, which is I comma k. That's kind of the whole method. Yeah.
Why do you subtract row elements individually, not as a whole, like row minus?
Oh, you mean the MATLAB? Well, so yeah, because I don't want to confuse things. This is not the way you do things in MATLAB. In a language like C, you have to do it this way. You figure out exactly what you do to each number, right? In the MATLAB code, you will never write like this. You're right. I'm just trying to be pedagogical in the sense that we unwind it. I mean, in fact, if you want to bring it either further, you will never write this code at all in MATLAB, because this is what MATLAB does. So we're just trying to be pedagogical. But no, in a C code, you wouldn't have vector operations. But yeah, it's a good observation. It's a whole vector minus a whole vector times something, right? Clearly, you want to think about smarter MATLAB operations. In fact, you can do one more step and say that this whole block here is a matrix minus another matrix. So you can do this really well. Anyway, that's the whole method. Just some details. Of course, you have to do the same thing to B. Bj has to be, you have to subtract m times bi from that. That's pretty obvious. And then you're done. Okay? So just think about that method. Let's look at back substitution. So then finally you end up with a method that is triangular. I'm going to make it, well, let's make it the same size. And of course you have a b here, right? So you have this system. Think about what back substitution means. I think you might agree. A famous saying in like computer science is that you don't really understand a method until you code it up, because there is no room. When you do it by hand, I'm sure you can kind of just play around with the equations. You don't have to be 100% systematic. If I give you a system of equations, you can kind of play around. That's probably what they teach you in high school. Somewhat systematic, but you can kind of get away with it. In a computer, if you mess up an I and the I plus 1, these details really do matter, right? So coding it is important. So let's think about back substitution. Again, if I gave you this, you would probably say, hey, I know x6, right? Because x6 is clearly just that b now divided by the a and n, right? That's how the method works. Now, that means that all of these multiples here can be subtracted from the right-hand side. But let's go one step at a time. So now I don't really know if this multiplies x5 plus this times x6, right? But I know x6. So you subtract it from here and divide by that number. Then you go here, and in a general row, there is no elimination here, but in a general row, we would have an I that is, for example, standing here. And that I needs to start at n. We start down here, and we actually need to go now all the way up to here. And you can think about that when we see what we do. Now, in the general case, what you need to do, you're standing at I, and you've already computed the x's above it, right? So we know, because when we're done with the I, we've computed that number, and then we go back up like that. So at this third step, we computed x4, x5, and x6, which means that you multiply it by these three numbers and subtract from there. That's another for loop, and that for loop goes from I plus 1 to n, and we call it j. And the operation is easy. The operation is that you take, might not be pedagogical, but I start by setting x equals to the right-hand side. It's wrong. I take this vector b that we produced, and I set it equal to x, and then I subtract. It just coding-wise, it ends up being notationally better. So I just subtract all of these numbers from that right-hand side. And at the end, all you have is the diagonal element ai that you have to divide by. All right? So please just spend some time looking at realizing that this can be done. I'm not saying these details are trivial, but you might appreciate the idea that you thought you knew an algorithm perfectly well, but coding it up can be a little tricky sometimes. All right, the next big part we did that was more numerical analysis based was counting operations, okay? And I'm not going to do it again. I'm just going to emphasize. So a typical question people ask themselves in linear algebra is, what is the cost of this method? I did a test in MATLAB that was not too persuasive because it was there were issues with the computer. What is cost in a computer? Clearly, we mean time in a way. But when we do calculations by hand and math like this, it's better to kind of standardize. We don't want to talk too much computer science special things. So what people do is that they count operations, okay? And an operation is basically plus, minus, times, or division, right? And you count the number of those, and then you can tell a little bit about the cost of the matrix. But you have to realize that sometimes a computer can make 1,000 multiplications faster than another times it just makes 10, because it's all about grabbing things from memory and things like that. So there are issues. But let's say we just count operations. That's a simplification here. How do you count operations? Let me look at a few special cases that show up. Trivial. If you have a structure of this form, and you do one multiplication, how many multiplications are you doing? Well, you're clearly doing n multiplications, right? That was easy. Let me do another easy case that we didn't see before. If you do a for loop there, and then you have a for loop here, from 1 to n, and you do one multiplication, how many multiplications are you doing? Well, you have to realize how for loops works. For each I, you're going to do all of these j's, right? Pretty obvious that you're doing n square multiplications, okay? Unfortunately, this doesn't fit our methods because we're doing other things. We're doing for I equals 1 to n. I'm simplifying now. Of course, our method went to n minus 1, which doesn't matter, but it just makes it one more opportunity for mistakes. And then we did a j that went from I to n. And we didn't do that either. We actually went from I plus 1. Doesn't matter. You have an I somewhere here, right? And you're doing one multiplication. How many operations is that? Okay? And then you have to think there's some of this. So I mean, you can just, it's not magic, right? When I is 1, you're doing n multiplications, right? When I is 2, you're doing n minus 1. When I is n, you're just doing one multiplication. So it has this triangular system. It sounds like it's divided by 2 something, a square divided by 2. But more generally, you're doing a sum from I1 to n. And at each I, you have to think about this. It's n minus I plus 1, actually. Look at the special cases to realize that. N minus I plus 1 operations. Okay? And this is not a form we want to leave it in. So we use some formula for that. And the 2 formula you're going to get away with are going to be the ones on the top, which tells you. So if you look at these terms here, I mean, a sum of n is trivial. This is n squared, right? Sum of 1s are even more trivial. That's n. The issue is the I. Okay? But we have formulas for that. For example, in this case, the first one up there. And then you simplify that, and you get that. And finally, the worst structure here was that we have a nested. So there are actually many ways to do this. But in our case, we had this type. We had the same j going from I to n. And then we had k. And you realize that there are many ways. There are algorithms here like Cholesky factorization where this k will start at j and go to n. That's another structure. But in our method, I took away the code. But in our method, we go from I to n here as well. And there might be plus and minus. This is not exactly what we did. But I don't really care about plus and minus ones. I mean, the structure is important. And you're doing one multiplication. What is the structure then? Well, it's kind of easier when you don't put the j here, because this is a pretty simple block. So you look at the sum. This is a little hard to do by hand. I mean, so when I is 1, you're doing n of these and n of these, right? So, you know, that sounds like, you know, you're going to do, for I equal to 1, we're going to do exactly n square multiplications. But then I becomes 2, then we're just doing n minus 1 of these and n minus 1 of these, so that's an n minus 1 square. It sounds a little bit like going from backwards, it's like an I square, sum of I squares. But you don't have to think that much. You could just write it up. And you can say, in fact, this would be much easier if I turned it into 1 colon I instead of, because now I get a lot of n minuses here. But for each I, we're doing n minus I plus 1 of these. And for each of those, we're doing that, right? My example was not like this because one of these was plus 1, so we had to write it. But anyway, this is what happens. When you expand this, you get a bunch of trivial constants. Remember, n is a constant. You get something multiplying I, just like here. And you're, of course, also getting an I square where you use the second formula. I think that's the worst we're going to show you, but you can all imagine that you can make this, if you come up with methods. Turns out almost every method in linear algebra is cubic or quadratic. Okay? So here are some simple control questions. And what you do with the at the end of the line is often you just want an order and maybe the constant. You want the leading order terms. Think about some linear algebra operations. A dot product, A dot B. Which of these patterns would it fit? I'm standing over here, and I start easy. So it sounds like I'm up here, right? How would you implement a dot product in a computer? You go through all the numbers in the vector, and you do something like the dot product is equal to what it was before plus AI times BI, right? So it's one multiplication. It's exactly this here. You're doing exactly n multiplication. It's pretty obvious, right? All right, let's go on. What easy linear algebra operation do you think this is? Or it could be many, but I'm thinking of something. Yes, it would be exactly matrix multiplication. You have to think a little bit about it, but if you do A times X, this is what it ends up being. If you turn this into plus, even easier, it would be adding 2 matrices of size n by n, right? So, you know, Why? Because there is no it's not a complicated algorithm. You go through, when you do matrix vector multiplication, you go through everything like this, right? It's n rows and n columns, you just do them all, and it's easy, right? Now, when you start talking about these things, you get reminded of these triangular structures in a typical Gaussian elimination. This here, of course, has the structure of the backward substitution that we did before. What is a better example? You could also argue that it has the structure of the divisions of the b's. The cost of doing the b's has this structure, right? But of course, the main cost is going to come from this row, which has the structure over there. So there are details. I'm just emphasizing what the structures are. But in general, the entire backward substitution has only 2 j's. And although, of course, I've flipped, it's very similar to this. I've flipped, of course, so I go from n down to 1. I mean, when you count operations, that really doesn't matter. And then I guess I do put an I plus 1. But this is really similar to backward substitution. And if you want to be fancy, and they are fancy in the book, you, of course, have to differ between the number of multiplications, subtractions, and divisions, right? And you can do them separately, and they have different structures. But that's the whole game. Let's see what we have in the slides for all this. There are things coming out of this. Often in this field, you combine multiplications and divisions and additions and subtractions because computers don't care. They are, in fact, nowadays, people combine all 4 of those. But in the old days, not too long ago, like 10 or 20 years ago, computers were much faster at adding floating point numbers. You know how hard it is to multiply. If I give you 2 16-digit numbers, you can add them in 30 seconds, right? Carries and just elementary school stuff. Imagine multiplying 2 16-digit numbers. It's the whole, the method, whatever. It's a lot more work. Turns out computers are kind of all equally. So in the old days, it was a big difference between multiplying and adding. Now it's not. But anyway, this book is not updated with that. It's OK. You can count them separately. But they merge them like this. When you put all this together, you get, I think the numbers to emphasize here are, actually here they add up. Also, do you want to add up the elimination and the backward substitution? Yeah, why not? And you get some numbers out. And it turns out that it's, of course, n cubed. That's the first thing to know about this, that it scales like n cubed. Double the matrix, it should be about 8 times more expensive. The next thing to remember is that the thing multiplying n cubed is 2/3, if you count both additions and multiplication. So these are numbers you know in linear algebra. And you compare it with another famous method called QR method that you might have just touched upon in Math 110. But then it would be twice the cost, and you would say, look, QR is cool, but it's twice as expensive. It's not fundamentally more expensive. It's just twice as expensive. Another interesting number you can put out here is how expensive is Gaussian elimination compared to matrix-matrix multiplication? So I never did that structure. But if I were to be really pedagogical here, I would do, you remember this was trivial because it was n and n, right? I could put another k here that goes from 1 to n. And the cost is, of course, n cubed. And if you remember a matrix-matrix multiplication, that's really just multiplying 2 n by n matrices. And that's n cubed multiplications. Okay? And if you want to count additions, it's also n cubed additions, which means that multiplying 2 matrices sounds like an easy thing compared to Gaussian elimination. But it's much more expensive because it's 2 n cubed. It's not fundamentally more expensive, but it's a factor of 3 more expensive. Isn't that amazing? So actually, Gaussian elimination, even if it looks complicated, since you're narrowing down, when you're done with the first row, you have done these 0, you narrow down like this, you get this factor of 6 or 3 coming out of it. So that's kind of interesting. Anyway, let's talk about pivoting. Here's a nice example of that. You all know that if a 0 shows up, actually the only thing that can go wrong here is that a 0 shows up. And when I say shows up, I mean on the pivot diagonal. So the worst thing here would be that this guy is 0. And what you do in Math 110 and Math 54 is that you find something down here that is not 0, and you switch the rows, OK? What if there are no non-zeros? What if they're all 0? Then you can't do that, right? What do? You don't do anything. You give an appropriate error message. And what was wrong with your matrix? What? That is correct. You can't make it upper. No, you can make it upper triangular. They're already 0s. You just move on if you want to do that. That's not the issue. It's singular, yeah. If you have the zeros here, you can look at some simple arguments to see that it's single. So we can assume that's not going to happen now, but of course that's an issue in the later on. Anyway, so a trivial example of that is I'm doing 2 by 2s here, but this is called pivoting. As selecting in the way of selecting the right pivots. So for example, if you take the simplest I can come up with, a 0 there, and the right-hand side of 1, 2, you cannot eliminate this 1 by the procedure we described, because basically you would be dividing by 0, right? But you just switch it. And when you switch the rows, of course, it's pretty obvious to see that you're switching the b's. Did I switch the x's? I did not, right? So x1 is still the number multiplied by this column. I didn't switch the columns, right? Another operation you could do, and it's sometimes done, is to switch columns. Then you're not switching the equations, but you're switching the unknowns x, which is not fundamentally wrong. You're just renaming things. We're not going to do that now. Anyway, when you come this far, clearly you can get x to be 1, and then you subtract here, and you get a 1. Okay? So that was easy. Now here comes the punchline. For numerical analysis. This seems like, I mean, what are the odds? Zeros are actually quite common in a computer because they are exactly represented by our computers, and zeros are just, they show up. But if you do a bunch of calculations and this 0 shows up further down, I could make up a matrix where there are no zeros, but after your elimination you get a 0. In the computer that would not be exactly a 0, and you know that. Nothing is exactly like that. So what if this is slightly away from 0? And clearly, in your hand calculations, it doesn't matter. The only problem was dividing by 0. And that's true. If you do this by hand with exact arithmetic, the only problem is 0. In a computer, since we cut off, there are other issues. So what you're going to see here is that you need to pivot even if AII is non-zero. And here's an example showing that. So I'm going to take exactly the same example, and instead of the 0, I'm going to put 10 to the minus 20. Okay? Now, suppose we're not pivoting, because we don't understand that it's a problem. So we say, this is all good. What is the m, the multiplier? What do you have to multiply this equation by, such that when you subtract it from here, you put a 0 there? It's, of course, like in the computer code, that divided by that, right? So it's 10 to the 20. You multiply this equation by 10 to the 20, subtract from here, you put the 0 that you want down here. All right? So let's do that. Remember, we don't touch this row, so I'm just copying it. There's still a 1 there. If you do it, you will actually, in principle, get a 0 here. That's not the problem. Here you will, of course, get 1 minus 10 to the 20 times that 1. You get 1 minus 10 to the 20. In the right-hand side, you get 2 minus 10 to the 20. All right? And now, of course, what I'm going to say is that if you do that right, it's not a problem. But you know what a computer does to this number, right? What is 1 minus 10 to the 20 in a computer? It's minus 10 to the 20. It doesn't see the 1. See it this way, you have this enormous number, negative or not, doesn't matter. And you're adding 1. You have 16 digits. You can't see this number, right? So this is the type of truncation we talked about before. It's not the cancellation. It's just adding. You don't have 20 digits of precision. So this will be approximately, in the computer, equal to, this is not a problem. Small numbers are not a problem. It's the precision that's the problem, right? So these are not the problem. In fact, this calculation was not a problem either, getting a 0 there. But this will approximately be minus 10 to the 20. And of course, the same thing will happen here. And here's the problem. That all the information was in the fact that there was a 1 there and a 2 there. That's a pretty big difference. Right? But now both of them are eaten up by this enormous number. So here you now just get approximately minus 10 to the 20 as well. Okay? And when you back solve here, you get an incorrect x that says that this guy here is 1. But, well, is that correct? All right, fine. But when you back solve, you got a, let's see what I'm doing here. Yeah, of course. You have a 1 here, and when you back solve that from the 1 there, you end up getting that this guy is equal to 0. Okay? Maybe that's an extreme example, but that's what we get out of this system. So we made that little approximative error, and that messed it up so much. Is this a small error? So you see the issue is that, I mean, you would expect errors if you have huge numbers and things are strange, but I don't. This is really just mimicking this problem. It's just that the computer accidentally put a small number there. It's so sensitive that if you change a 0, everything is order 1. But if you do a small perturbation of the 0 to 10 to the minus 20, the solution changes completely by 100, order 1, right? That's just not acceptable. So this is a big problem. One solution to this is to do exactly what before. And it's called partial pivoting. And remember what I said before. You want to find, if you had a 0, you find a row below that has a non-zero, and you switch. You know how we extend it to this case? Well, I mean, they are all non-zero. It's a tolerance. The issue is that we divide, that the multiplier got very large. I don't like having 1 over 10 to the minus 20, which is 10 to the 20 to multiply. That was the problem. So I'm going to switch rows based on trying to make that not so large. Another way to say that is that I want to find the largest element here. That should be my pivot. You want to have the largest number up here. Okay? Quite simple. And we'll do it. Find largest pivot element. Pivot element. So in this case, that means that the first step you're doing when you see this matrix is going to be that you switch rows. 10 to the minus 20, and then there was a 1 there. Okay? What happens now? Let's see that this is not a problem. We don't touch the first row. I need more space. We don't touch the first row. But the second row will say that you need to multiply this row by 10 to the minus 20 and subtract here to put a 0 there, and that's going to work out fine. This number will, of course, be 1 minus 10 to the 20 minus 20 times that one, right? So it's 1 minus 10 to the minus 20. This guy 1 here will be 1 minus 2 times 10 to the minus 20. All right? Now, of course, the computer will still make mistakes. But the algorithm is not so sensitive to it. I'm going to have to move over here. And when you do the approximation, I'm going to do the approximation again. And say that this, I now say, is approximately equal to, of course, still just 1, 1, 2. And here you get your 0. Now, 1 minus 10 to the minus 20, just like before, that's 1. You can't see the 10 to the minus 20. And the 2 is actually 2. No, it was a 1 there, too, because I switched rows. Sorry. All right, and now you can solve for an x that is approximate. Well, of course, in my example, it happens to be exact, but that's luck. I mean, you will get tiny errors in general, but they will not blow up like before. It tells you that x2 is equal to 2, and x1, back solve here, you get 1, which happens to be much closer to that. This is the general procedure. So in a one-liner, it's very easy. The one-liner is you need to pivot numerically all the time. It might not be as extreme as this, but it adds up. Partial pivoting is this concept here. So my code is a horrible thing, and a lot of people do these things in computers. You kind of get away with it for small matrices, but this code here would be really scary in any production code. And even if you say no 0, even if you put, maybe you would say here, the only problem with this code is that number, right? And you would say, what if I don't put an if statement to tell me if it's equal to 0? A lot of people do that, and they see like, OK, it's never 0, I'm fine. No, you're not. You've got to do this because you get errors that you can't really see if you don't do it well. Let's see how I summarize it in the slides. Here's a whole slide about it. In Gaussian element, if a pivot element, this is a notation, let's not worry about the iteration, this is the iteration number. If a pivot element is small compared to an element before, which we did here, the pivot element is small compared to the element below. The multiplier, 1 divided by that, will be very large, and it causes bad round-off errors. And partial pivoting is what I described. You find the largest. So this was just a 2 by 2, so in this case it was easy. I found that guy and flipped it. If you have a big system, you look everywhere below. and you get to take the largest one. Because I could have a 10 to the minus 10 coming down here, right? I don't want to flip with that one. This could be 10 to the minus 10. I would still flip with it. But if there's a 1 there, you got to pick the 1. You got to pick the largest one. That's a simple algorithm. Let's look at the code. I'm not going to code it from scratch. I'm just going to open it. So this is on the web page, and it's just called Gauss elim. It should be very similar to the code I wrote before, except for this little chunk here. Let's just confirm. It's very similar, except less spaces. But this is very similar to what we did before. Let's just update it to do this thing. Well, so how does this work? Let's say the very first step, but it's actually going to be done at every step. Before you start putting zeros below a pivot, you got to do this operation. And the operation was look at that whole line. You can think a little bit and realize that these are the elements we're considering. Maybe I need a better figure for that. So when you're at a state, let me do one of these again. You've done a bunch of elimination, and you're standing here. OK? You know what I mean by this? You've started doing Gaussian elimination. Here is stuff that I don't care about. But you have this structure, right? Before you start eliminating these guys, you got to look at all of these guys to determine which should get the honor of being the largest element up here, right? This is A. We're standing at column I, of course, and row I down to n. So A of row I to n, comma column I. These are the numbers I'm considering. This syntax, computer scientists won't like me, but I just want to know where it is. I don't care what it is. I want to know where it is, and I call it P. So maybe if this is 10 to the 20, this will be my P, right? My largest row. And then it's pretty easy to tell MATLAB to take rows IP and make them equal to rows PI. That's the same thing as saying flipping rows. When you flip rows, you're flipping equations. Don't forget to also flip the B's, which is the next line. So not too complicated. And actually, this might be a little tricky, but since I'm grabbing this vector, now this became numbered 1. So when I actually flip, it has to, of course, add 3, right? So that's what I'm doing here. Anyway, 4 lines, maybe a little cryptic, but it's really just doing that. Yeah? Nothing. It's a computer science word for I don't care. Actually, MATLAB has they realized that people wrote this, and it just makes the code ugly, so they have, more recently in MATLAB, implemented this, I think. So if you have a vector, you can do max of the vector, and you get the largest number. I don't want the largest number. I just want to know where it is. And then there's a second output as an index, which tells you where it is, and it tells you, let me just do this. I always forget this. So you can just run max, and you get the number. If you ask for the second output, they tell you which one was. In this case, it was the 4th one, right? I don't want to know. I just want to know where it was, which is the same thing, but I really don't want to see the maximum number. And you can put a twiddle there. So that's the way to do it. Of course, you can call it foo as well, or dummy. Well, that's the code. So this is the code, and almost exactly what is done in backslash in any state-of-the-art anything, except that, of course, these things you don't implement in MATLAB. That's a different discussion, but if you're a computer scientist, you know that MATLAB, the way it works, it's interpreted. It has a memory allocation principle that makes this magnitude slower than a C code. So it's done in the backslash code. But in terms of algorithm, it's really the state-of-the-art. Here's just one thing that I mentioned in the book that I kind of agree with. If you look at a linear system, let's say this guy here, or anyone, right? It's a set of equations. And just, it might be such that you accidentally multiply this equation by 10 to the 20, OK? Because maybe you chose the wrong units. Maybe this here tells you the conservation of momentum in SI units. And here, accidentally, you did, joules instead of electron volts, and it ended up being 10 to the minus 20. Things are just poorly scaled. You realize that in the terms of if you have a bunch of equations, scaling doesn't really matter in an exact arithmetic. You can take any of your equation, you can switch units, you can multiply by 10 to the minus 20. It's the same equation. Nobody cares. Well, the computer will care, because all these pivots will be messed up. Okay? So a great first step to do, actually, sometimes it's not quite what I'll be describing, but a great first step is to say, why don't we just make all rows kind of order 1? right? And that's sometimes called a preconditioning or pre-scaling. You go through and look, what are the, if all these numbers are 10 to the minus 20, let's just multiply them by 10 to the plus 20, right? So that's an operation you could do beforehand. They describe it a little bit differently here, where they say that it's called scaled partial pivoting. Go through the matrix and look for the largest element in each row. So in this case, that would be 1, 1, 1 for each of them, and there is no issue, right? In this case, it's also 1, 1, so it's not an issue. This matrix is poorly scaled, but that's because we started messing with it. But if you accidentally multiply this row here by a large number, then this S for that row will become large. And what they're suggesting is you don't really have to modify the equation. Just change slightly the method by which you pick this largest p here, such that if this entire equation is multiplied by a big number, then you should divide it away. You should pretend that you divide it by that large number s. So you do that on both sides, and that's what you base your partial pivoting on. Kind of nice. You don't have to mess up the equation, but this is what controls this accuracy check. That if this entire equation has large numbers here, it's not going to be a problem, or that you subtract by it. So then you don't have to choose it. But anyway, that's what comes out of it. I think I signed one example of that. Just use the formula and see. This is compared to the previous step, this is a detail. This is a scaling thing. This is a practical detail. But in a real computer code, it has to be done. Anyway, so I don't think that was review for you guys. That was new stuff, right, to some extent. Maybe not the row change, but the idea that you do it no matter what. Did I change? How about the operation counts now? How bad was this? Well, in terms of operation count, it's nothing. You could argue that finding a largest element is an operation, but it's almost nothing. I look at, just a few. It's nothing compared to the rest, right? In practice, of course, this is horrible to do in a computer. Switching rows is moving memory back and forth, which is much worse than multiplying numbers. And they don't like it. So in practice, you're coding this in an obscure way where you actually don't move it, but you have another index array that tells you that you flipped it, so you do the right thing. And so it's a practical mess, but not in terms of our calculations. There are no operations, basically. There's no times, no add. All right, that's 6.2. Moving on with 6.3. This is really a review. Math 110 students, I mean, if you really knew this, this would be very boring. But it's important, so you might want to pay attention anyway. Math 54, you will, of course, know everything on this slide, but maybe it will. Some of the proofs are not so rigorous in Math 54. I don't know. I've never taught Math 54, but I know they're not. They're more about doing than understanding. Anyway, you know what a matrix is. What does it mean for two matrices to be equal? For each index ij, it has to be equal to b, right? But in addition, the sizes must be the same. Right? Then two matrices are equal. If you have this, two matrices have the same size, you can add them, and it's defined by taking each entry and adding. Pretty easy, right? You can also define what it means to multiply a matrix by a scalar, and it means that you multiply each of the entries by a scalar. All right? High school material. Moving on. These are also fairly straightforward. Addition commutes, and it's associative like this. You see, for addition, this is trivial to prove, because addition is defined by just ignoring the matrix and looking at each number specifically. There's no communication. If you add two matrices, entry I, j here looks at I, j there. There is no communication between the, it just follows directly from the corresponding properties of the real numbers. You can add a 0. What do I mean by adding 0? What must this 0 be from what I've said so far? It must be a matrix, because I haven't talked about taking, this is confusing in MATLAB, because MATLAB will happily let you take a matrix like this x and add a 0, right? But you have to define what you mean by that. What does it mean to add a scalar to a matrix? Well, clearly it's obvious what they mean. But if you have an actual, just a little MATLAB warning here, if you have an actual matrix here, a very common operation in when you compute, for example, eigenvalues, which we'll do later, is to do I minus some lambda times a minus times I, right? And many people think scalar and just do this. Is that correct? It will subtract lambda from all the elements. Remember, I only has ones on the diagonal. Very common MATLAB mistake. So anyway, this 0 is a matrix, and it's clear that this comes out. You can negate the matrix. You can multiply. It distributes like that. All is trivial. There's an identity here. Actually, in this case, of course, this is a scalar, this 1. Okay? We define what it means to multiply a matrix by a scalar, right? And it comes out easily. Anyway, let's move on. Matrix multiplication you should also know, but now it starts getting more interesting. It's defined in this way. You know how to do it. Don't forget it. Don't forget this expression. It's very fundamental. Maybe one of the main things is that it cannot always be done. The matrices must match size. If everything is square of the same size, which is a common special case, everything is n by n, then you can do whatever you want. But in general, you have an n by m matrix A and an m by p matrix B. These inner dimensions, the number of columns of A and number of rows of B, must match. Otherwise, it's not defined, and it doesn't work. In particular, if they are different, most likely, if AB works, BA is not defined. Okay? So as a special case, you see that they don't necessarily commute. Anyway, the definition is clear. We're going to use this expression a lot. And you know how to do it just monotonically by just doing, it's a bunch of dot products, by the way. Row I of A, column J of B, dot product with a temporary index K. That's how we describe it. Some special matrices that we already talked about. Square is a very important special case. Our linear systems are often square. Then you have the same, well, it's obvious what it means. A diagonal matrix is square. Not necessarily always the definition people make, in particular not MATLAB. MATLAB is happy to give you a diagonal matrix using diag command that is 10 by 5. And you can think about what it does. It does exactly this. It puts numbers on the diagonal, but it's just not square. But in this book, we follow this definition. A diagonal matrix is square, and it's almost zero. It's zero almost everywhere, but not on the diagonal, which is, of course, this line here where I is equal to j. Identity matrix is a diagonal matrix, and it has 1s on the diagonal. Here are terms that are very often used in numerics, so maybe that's a new term for you, but it's pretty obvious. An upper triangular matrix, n by n matrix, U, is defined by being 0. And if you think about this expression, it says that if the row I is greater than the column j, and then you realize after a while that that means, hey, I'm down here. I have an II, and then the row is greater. It means I'm below the diagonal, not including the diagonal. So as a particular case, if I should just get you prepared for what's coming later in this course, after Gaussian elimination, we have this type of matrix, right? That is an upper triangular matrix. Because whenever the row is greater than the column, it's equal to 0. Of course, you can define a lower triangular in the same way. All right, now it's getting a little interesting. Properties of matrix multiplication. It is associative in this sense. And let's look at where that comes from. Yeah, that's a nice little exercise. These properties are more straightforward, but they have to be done. But B is easy to prove. C is easy to prove as well because of the very simple structure of I. It's just a bunch of 1s on the diagonal. But again, if you accidentally think, suppose you're all new to this and you haven't seen linear algebra, you might think that the identity would be a matrix with all 1s. I mean, it's so obviously wrong for you. I'm just saying, if I just take a bunch of good high school students who never seen this, I could probably trick them into thinking that the identity here is 1s everywhere. But then they will run into trouble. But it has to be our identity, which is a diagonal matrix with 1s on the diagonal. What else? Multiplying by scalar is also trivial. Maybe the only non-trivial one is this one. Let's prove it. Just you see the operation when we prove these things. And as I said, this is really stuff we do in Math 110 all the time, but maybe not in Math 54. The general procedure for proving something like that is to just go back to the definitions. So you want to show that multiplying 3 matrices is associative in this sense, okay? Now, just to start really silly here, we did define what it meant for 2 matrices to be equal, right? So the very first thing you must ask yourself is, what does that mean? Okay? Well, it means that they're equal, right? But what does that mean? It means that each entry is equal and they have the same size. So you might want to start by checking. You see how we accidentally could actually check that all the numbers we think are there are equal, but then the sizes are all different. We padded down a bunch of zeros or something. Then they would not be equal. So you got to check the sizes. Dimensions. So in general, we will have an A that is n by m. We will have a b that better be m by k, and we will have a c that better be k here and something else there, right? That's what we have. I say better be because if that's not m the same, and if that's not the same, you cannot do it, right? And of course, if you really want to be strict about this definition, this is the case when either of them is defined, right? But you know, if they're not defined, you can't even do it. So let's check the dimension. So a times bc. Well, this here is bc. That's an m by p, right? But this here was, as we said, an n by m. So this here, the m's eat each other, and it's n by p. So it's clear that the multiplication is n by p. We eat all the inner dimensions, right? But then you might want to check that ab parenthesis times c gives the same thing. And indeed, this is n by k. But this guy was k by p. So they, again, eat each other, and it's n by p. OK? That's the first step. Kind of silly, because you would likely discover this later on when you do the checking the entries. If that was not the case, but you know, it doesn't hurt to spell it out. All right, now comes the hard work, the numbers. So why don't we look at left-hand side ij? So we look at a typical entry of the matrix in the left-hand side, okay? And we realize that it's, of course, if you want to go really slowly, it's a, b, c, and we mix parentheses with brackets, just so we get some variation, and that's what we want, right? And now you start on nesting. The first thing you see is a matrix multiplication of two matrices, A and BC, right? And you plug in the definition. And you might not, I'm going to choose good variable names here, so things work out. But if you don't do that, you have a little struggle identifying things at the end. But you have some index. I'm not going to call it I now, because I'm already using I and j as the number I'm looking at. So this matrix multiplication better have something else. Let's do S. From 1 to m, the number of columns of A, and you do a dot product where you take the first matrix, and I'm going to use the MATLAB notation here, AIS. Remember I said before that it's very common to turn it into a lowercase a, but you know what? That wouldn't really help me for this guy anyway. So I'm just going to use the MATLAB. This is pretty clear. And this is just another matrix, index Sj. Okay? Next step, well, we still don't know what this is. We want to unwind all of this, so now you do it again. And you need new names. But this we just copy, AIS. And then there's another matrix multiplication. You want entry Sj of this matrix, which is, if you just plug it in and you're careful, it has to be a sum going over the k rows of B. Sorry, k columns of B and k rows of C. And you need a new index, let's call it L. So you need L from 1 to k. And this is, of course, going to be B, the row that you want, S, and the temporary index, C, temporary index, and the column that you want. And you can put the parentheses here for now, if you want to. But, you know, sums are well behaved. You can move things around. There are some nice properties. So all of this can be written as I goes from 1 to m. L goes from 1 to k, and we get these three factors. B, AIS, B, S, sorry. So are we, the temporary index was L. L goes from 1 to k, and you're picking the Lth column of this times the Lth row of that. So SL, and here's CLJ. All right? Why did I do it this way? Well, it's the way I chose to prove it, and I'm going to do the same thing with the right-hand side and show that it's the same. Of course, you don't have to do that. You could go either way. This is kind of a very down, it's the same thing as writing out all the little scalar operations you would do. There are no matrices left any longer. I mean, there are matrices, but this is all scalar operations, right? So it's a kind of a normalized way to write it, and if you do the same thing with the right-hand side, it should come out the same. So, you know, these are pretty boring proofs. But just quickly, the right-hand side, ij, would then be the other way. Previously, we did BC, so now let's do AB like that, and the C, and I guess I need that one, right? And then you just do it again, choosing. And now I'm a little smart here, choosing the L first. Normally, you would not. If you do it first, you would probably call this S like before, right? But I know there's going to be flipping happening here, so we can identify. At the end, you might have to match variables having different names. But anyway, you have the matrix AB. You have the entry. You want the entry ij of this, right? So that's going to be the row I and the temporary L. And you have C is going to be Lj. Then you apply it again. You get this L from 1 to K. And then you get, now I'm going to call it S, of course, because it goes over the M rows here. And we're getting A, the row that we want I, times the temporary index S, B, S, and there's the column row, and we can put that parenthesis. And the C, we didn't do anything with. And this should be the same. All right? So it's a sum of, why don't we just flip it? And I want to point out that it looks trivial right now, but if you did choose, I mean, the first time you see a matrix vector product, why would I now flip it, right? You would probably have called this S and the next one L or something, right? Consistently to before. So what you have to do when you identify that these are the same is to rename things. But you know, in this case, it's pretty clear that that's the case, okay? So now you check the dimensions, check all the entries using the definitions. Pretty straightforward. All right, anyway, so now we know that, and we're going to use it later. Let's talk about inversion. What does this mean? You cannot talk about an inverse if it's not square. There are extensions, but no. If we talk about inverse and it's not square, it's an error. It's like multiplying with the wrong dimension. Everything is wrong. You need it to be square, and the inverse might still not exist, as you know. That's what we call a singular matrix or non-invertible matrix. But if it does exist, we label it A to the power of -1, and it has this property. If you do A times it on either side, you get the identity matrix Z. And that's the inverse of A. All right? Some nice properties that you might take for granted, but you should probably reflect over a little bit, is it's unique. Do you know the typical way to show uniqueness? How do you start uniqueness proof often? Yeah, suppose you have two different ones and do some trivial operations and see that they end up being the same. So how do you show that A inverse is unique? Well, you suppose that you have two inverses, and I'm going to confuse you by calling them B and C, are both inverses of A. Well, what that means is, then you write down everything that means. That means that A multiplied by B is identity. But also, and this is another property, B times A is also identity, right? Same thing with C. Okay, and of course, you got to turn this into a relationship between A and B, sorry, B and C. And as the theorem suggests, we should get that they must be equal. And you can do a little calculation like this. There are many ways to actually do this, but you take the C, you multiply by an I, because you know you can do it, because that's something we didn't prove, but it was on the previous slide. Now you take this I and replace by something involving B, for example, CAB. Guess what I'm going to do with this guy? What we just proved, right? So that is associative. So you say CA here, and you get your B out there. And then you go up here, there, and see that that's equal to I. So this is IB. And then you use the same as before to show that's equal to B. So therefore, they must be unique. What else? What is the inverse of an inverse? Well, it says there. You get back to where you started. Do you take that for granted? It's actually very easy to see that that must be the. I mean, I know you probably think of it in terms that, you know, an inverse. There's so many other cases. Like if you do 1 over a number and you do 1 over that, then you get back to where you started if nothing is 0, right? But you know, strictly speaking, there could be a long sequence of inverses that didn't have that property. But there cannot, and here's the easy way to see it. The inverse of an inverse is equal to A. Why? Just look at the definition of an inverse. Okay? So this is, you're clearly, except if you want to be really super careful here, when inverse exists, right? So we don't say that here, but yeah, it does say that for any non-singular matrix A. So, so then we know this is true, right? If you just look at this, you have the proof. But you have to see it differently. What you think is that you have a matrix A, and its inverse is this matrix, right? By the definition of inverse. All right? What if you look at this matrix? This is a matrix that you have, and you like it, and call it B. What is its inverse? It's A, right? From the definition, because it's fixed. So that's how easy you can see that that must be the case. So A is an inverse of the inverse. Okay, I emphasize this because, you know, if you have a theorem saying equal, it means that it cannot be anything else. Could there be many inverses? You need to use the result in A to say that uniqueness implies that it's equality, right? Is equal to I. Well, sorry, is equal to A. You know, it's a little over careful, but clearly we only showed that we had one inverse here, but they're unique, so it's fine. Here's something you do all the time, and it's of course very similar, and not to be confused with the corresponding result for transposes. But it's interesting that they flip the order when you want to distribute the inverse across these matrices, right? How do you show that? AB inverse is B inverse A inverse. Well, here's the good news. If I tell you that a theorem, anything about a matrix that you have, AB, and I tell you what the inverse is, really easy to check that it is indeed an inverse. From the definition of inverse, you just multiply them, right? So the way you start this, I'm just saying, I mean, I could just do it. I'm just trying to give you an indication. How do you start a proof like this? And what I'm saying is that it's a statement about what the inverse of a certain matrix is. If you want to prove it, you just plug it in to the definition of inverse and say, yeah, it worked out, and therefore it's an inverse, right? So what it's doing is really saying that this here, it claims that that is an inverse of the matrix AB. Right? It claims that if you take the matrix AB, an inverse of that is equal to B inverse A inverse, right? So if you take this B inverse by A inverse and multiply by AB, it should be equal to I. And that's what we're looking for. To do that, we need some associativeness. And let's see what we want to do here. Clearly, you want to reshuffle these parentheses in a way so you can get these A's together, right? So why don't we put the parentheses like that? And then we have the B there. Because now, you know, clearly this is the case when these are non-singular and exist. You can get an I coming out of that. There was an inverse there, of course. This is BI, B inverse. The inverse is on the first B. All right? But that's B inverse B, and that's I. So, you know, it's fairly straightforward to show that. Do I need one more step? Strictly speaking, I just showed, just like here, that this is one inverse to this guy. Sorry, this is one inverse to AB. To know that it's the inverse, you need uniqueness. Let's just say uniqueness. Gibbs theorem. Right? You need that again. All right. Easy enough. Moving on. What do we have here? We have a matrix transpose. It's pretty obvious what it is. You need to flip the dimensions, and you need to flip the indices, right? You can imagine any proof involving this will just flip indices every time you see a transpose. In fact, when you go into entry form like this, suppose that this was instead the transpose of AB, you can just take away the transpose. Suppose I put a transpose there. You have to be careful with parentheses. But suppose I put a transpose on this matrix, and then I take entry IJ, IL. I just remove the transpose and flip them, right? So that's what it is. And the dimension calculation, of course, has to be carried out as well to make sure it works. But that's what it is. Here's a term we'll be using a lot later. Symmetric means that the transpose is equal to the matrix itself. All right, some theorems here. ATT equals A, completely trivial. But strictly speaking, it's an equal sign. You must make sure they have the same dimensions, of course, because you flip NM to MN and then back. You must see they have the same entries because you flip and then you flip back. This is also very easy because addition is as the way it is. The next two are not so directly trivial. The C one there we use all the time, so let's look at it, where it comes from. C. When you multiply transposes, when you take the transpose of a product, you get the product of the transposes in the reverse order. So AB transpose. By the way, I think it's really annoying with small t, but we can stick to it. I don't know. I like the big t's. But I'm going to try to do it the way they want. Why is this the case? Because, how do you prove this? This is really just back to the definition. Go back to the entry-wise form, right? You could, if you want to, start by the dimensions. And then you can convince yourself fairly easily that this has the dimensions of the number of rows of A by the number of columns of B flipped, right? So I guess it has the dimensions of the number of columns of B times the number of rows of A. Here, clearly, this has the number of rows of B transpose with this number of columns of B. So you can convince yourself about the dimensions. So let's just go at the entries. So you look at the entry IJ of this matrix. As I said, you have to be really careful with parentheses. If you really want to be super clear, you should put another bracket. So basically what I'm asking, am I taking the entry first and then transpose, or the other way around? And why do you think I think it's clear what I want? But it's not a mathematical argument. I was saying just so I can be sloppy and not put an extra parenthesis. That suppose you take the index first and then transpose. That's stupid, because that's a scalar. I'm not saying it's wrong. The transpose of a scalar is a scalar, but I wouldn't do that. So what I mean is AB transpose the ijth index, okay? Just warning you about that. All right, how do we do that? You just, well, we know what the product is, but you want the transpose of it. So the first thing you do is to remove the transpose and flip the indices. Now it's a product. So now you go back and say that's a sum from, I think I want an S now, from 1 to what? Well, the number of rows of K, of A, which is let's say it's equal to K. And then you do A of J, not I. If you blindly use the definition, you would probably call that an I because you're so used to it. We flipped it because it was a transpose. This is not a K, this is an S. And here's B, S. And then we want the ith column of B. All right? And then you have to look at what you want. You want to show that this is equal to something involving these individual matrices transpose. So it should be pretty clear that the next step now is to put the transposes there, right? Just put them there, but of course then you have to flip the indices. I, yes, right? And again, I'm kind of making it a little ambiguous what I mean by this. But it wouldn't make sense to ask for the sjth index of A and then do a transpose. But it's perfectly valid, so it's not clear what I did. But anyway. And now, of course, you can almost identically, but if you really want me to write it in the form that you like, you want the first matrix to the left with the I index there. And then you want the next one with a J index on the columns. And now we're comfortable to say that this is a matrix product. This is basically equal to the matrix product between B and transpose and A transpose, and we're taking the ijth index of that. So basically we show that the ijth index of one side, the left-hand side, is equal to the ijth index of the right-hand side. That's kind of, you have to be careful with that. Finally, what do we have here? If A inverse exists, then the transposes jump like this. And in fact, you know the notation we often use, it's minus t. But the fact is that since it doesn't matter, you can just go straight at that. And that comes from, just from completeness, we'll do that one as well. And then I'm done with proofs. So just bear with me for this last one. You want to see that it doesn't matter in which order you're doing inverses and transpose. So we want to show that you can just as well do the transpose first and then the inverse. Okay? Well, again, is this a difficult proof? I'm claiming that I have an inverse for you for a matrix. You just plug it in and test it. In fact, I'm claiming that the inverse of this matrix is that. Right? So what you do is that you take that matrix and multiply it by the suggested inverse, which is A inverse transpose. Okay? If I show that this is I've certainly shown that this is at least one inverse to this matrix, and then we'll use uniqueness. Of course, to do that, I want to put these t's together, so I'm going to use that and go backwards, right? And then I have to flip them. So this is A inverse without a transpose times A without a transpose, and then we put the transpose there. But this is I transposed, which doesn't matter. It's I. So the conclusion is that this matrix here, A inverse transpose, is an inverse of AT. Okay? And then you plug on uniqueness there. Uniqueness gives what you want. Right? All right. Enough with those. A bunch of nice properties. Let's talk a little bit about how to calculate an inverse. I don't have any slides on it. You know how to do it, but let me remind you. And by the way, one thing we'll come to very soon is just to, I don't know if you picked that up in math or anything else, but inverses we never use. It's funny that it's such a fundamental thing in the linear algebra education. And then when it comes to a computer, you can just not create an inverse. It's a horrible matrix. It has a lot of bad properties. You don't want the inverse. You do something else called factorizations. We'll come to that later. But calculating inverse matrices. So A is n by n. You want to find a B such that AB is equal to I. Sometimes it's nice to put a size on the I. If you know your matrix multiplication, you know that each column of B can be treated independently. And this is actually n. This is a linear system of equations, but it's actually n of them with n different right-hand sides. That's the way to see this. If B only has one column, then B is a column vector, right? Then it's really just AX equals B. Sorry, I shouldn't call it B. AX equals the right-hand side, right? Now there are many of them. That's fine. It's just a bunch of right-hand side vectors. So n linear systems. You could. This is n linear systems. Okay? With the same matrix A. How do we solve linear systems? Well, maybe Gaussian elimination, right? That's all we know so far. We take the matrix A and we augment it by the right-hand side that we used to call little b. Okay? What is our right-hand side? Remember, the b is kind of our x, but it's going to be many of them. The right-hand side is I. So that's why you put an I here. This is the system you want to solve. You want to solve the system A x equals I, right? Or if you look in vectors, A times the first column of B equals to the first column of I, etc., etc. And then you do all these elimination steps. Elimination, and you're getting something like this. What do I mean by this? I mean that U has now become triangular, and Y is completely messed up. Sorry, I has been completely messed up, and we call it Y, right? Now, if you want this to happen, you better solve it. You really want the x. You got to solve the whole system. So you solve now, and that's what we call back substitution. And then you will get b coming out of it. Basically, you will get, well, you don't have to make it an I if you don't want to. I would say you just, it depends on how you do it. But as you take this, these end right-hand sides and do the back substitution, out will pop. So that's the you've done this yourself many times, I think. So a routine question is, what is the inverse of this matrix? And you know what to do it. The only thing I didn't have time to show here is just the inverse of a very special matrix, which is a nice exercise on this here. Namely, if you have a 2 by 2 matrix, you can do a general 2 by 2 matrix. Of course, we insist that the determinant here is non-zero. But if it is, then A inverse can be written as 1 over the determinant times. And do you remember these ones? You flip the diagonals and you negate the off diagonals, right? Whatever way you remember that. But my plan was to just show this explicitly by doing these steps. Very easy. So it's not a big deal. But you've seen that before, I'm sure. It's kind of nice. If you have a 2 by 2, you can just write down the inverse if it exists. All right, that's a lot of linear algebra. Any questions? How new is this? I mean, you recognize a lot, I hope. At least this last part, right? I don't know why we teach it in every class. It's because it's important, I guess. Don't trivialize it. If it's completely trivial, you're fine, but pay a little bit of attention to it. Otherwise, you miss something. I have office hours now. Thank you.